Can you balance a 20p on a lemon and win a pint? And that's a question that I am asked every day, much like, would you like a bag with that? Are you going to use the microwave next? And Douglas, would you please leave us alone? But much like the answer to the question, Douglas, would you please leave us alone? The answer to the lemon question is no. And let's see why.
You see, no matter how much I try, you can never quite place the 20p directly over the lemon's centre of gravity. And because the lemon has effectively no form stability, it just rolls straight over if there's even a tiny imbalance. Damn, see? Can't be done.
Now what I said before isn't strictly true. A lemon does have some form stability. That's because its cross-section isn't a perfect circle. An ideal lemon, the one that we're going to be using for the maths later, does have a circular cross-section, but this one has imperfections because it's natural. But you can see I've marked the top with a Sharpie, and if I poke it just a little bit and introduce a heel, you can see that it returns to the upright very slowly because it doesn't have a lot of form stability, but it has a little bit.
Right, at the moment our ideal lemon can be thought of as having a circular cross-section. Bit like that, imagine it's a circle. And the waterline is going to be somewhere around here. The centre of buoyancy is down here in the centre of the underwater volume, but the centre of mass, the centre of gravity, we're going to assume as being higher and in the centre of the lemon. So buoyancy and gravity are here. Buoyancy is acting up and gravity is acting down. And that's all well and good. That's how a normal surface vessel would float. But now we need to imagine that we have introduced a coin to it. So if we draw it again, we'll do it over here. Maybe I should have done this bit before I drew on the lemon, because I may have buggered up the Sharpie, but let's ignore that. We have our lemon, and we have our coin. I'm going to draw it at an angle, and I'm going to exaggerate it a bit just to make it easier to look at. But because we can never place a coin perfectly squarely, going to have it at an angle, a bit like this. That's our coin. It has a reaction force, a bit like that. The centre of buoyancy is down here. But the centre of gravity is over here somewhere. It's been moved by the coin. Now, even though the centre of gravity of the lemon hasn't moved, the centre of gravity of the system has. That's because the coin is being held onto the lemon with friction, and until that friction is broken, they are to be treated as one body. So we can say the centre of gravity for the whole body is over here, and it's acting downwards. Now, because the centre of buoyancy isn't going to move, because we're imagining the lemon as being a circle, which it effectively is, especially when you've got a mass as big as a coin affecting it, we can see that there's a turning lever here, and that's going to tip the lemon off. Then eventually the lemon will slide off, gravity will move back to where it was originally, and the lemon will return to how it likes to float on its own, and you've lost 20p to the pub landlord. We can now have a look at when the coin is going to slip. Get rid of that, save it for later. So we're going to approximate the slope that the coin is sitting on, the slope of the lemon, as a straight line, because you take the average of it and that's effectively what you have. So I'm going to draw this over here, and I'm exaggerating it just to make it easier to draw. So we're saying that's the slope of the lemon. Obviously, this is theta. This is our coin. The reaction force for the coin is R. Friction is going this way. And the force of weight, which is mass times gravity, is going downwards. So we need to resolve these forces, of course. For that, we're not going to resolve it how you might imagine you would, vertically and horizontally. We're going to do it parallel to the plane and perpendicular to the plane, because two of our forces are in those directions and only one of them is vertical or horizontal. It just makes the trigonometry nicer. So first we're going to resolve the forces perpendicular to the plane. So we're going to pick this as our positive direction, and we're just going to have to do a little bit of trig with the gravity here. So this is also angle theta in there. So what have we got? So force R minus the force of mg cosine theta equals 0. I should say this is at the slipping point. So this is just when the coin is about to slip. And we know that at the slipping point, F is equal to the coefficient of friction times the reaction force. This is going to be important later. And then we have to resolve the forces parallel to the plane. Going to choose the F direction as positive, like this. And we can see that F minus mg sine theta equals 0. I'm just going to pause here and get a better pen. Right, I've switched to a normal pen now, which isn't as good for the camera, but I think I've killed my Sharpie by trying to draw on a wet lemon. Not something I expected to be saying this morning. Yeah, so we've got these two forces, which is nice, and we've also got F equals mu R. So what we want to do from here is find the angle at which the coin starts to slip. And we can do that fairly easily. So first I'm going to take equation 2 here. I'm going to label them equation 1 and equation 2. Can you see that? Yes, you can. And we're just going to make them look a bit nicer. So R equals mg cos theta and F equals mg sine theta. Because we're at the slipping point, I've said that, we know F equals mu R, so we can say that mu R equals mg sine theta. Now if we get R on its own, we have R equals mg sine theta over mu. Now we can combine these equations. We know R equals mg cos theta, and we know R equals mg sine theta over mu. So that must mean that mg cos theta equals mg sine theta over mu. That makes sense. We've got mg on both sides, so we can cancel them out. So now we have cos of theta equals sine of theta over mu. If we times both sides by mu, then we get mu cos theta equals sine of theta. And then we can divide both sides by cosine and get mu equals sine theta over cos theta, which doesn't look nice. How do we resolve that? Well, we know if we do some simple trig that we can make this a hell of a lot nicer. What do we know? We'll just do this over here. We know that sine of theta equals the opposite over the hypotenuse. And we know that cos theta equals the adjacent over the hypotenuse. And we know that tan of theta equals the opposite over the adjacent. Nice and easy. So if we have sine theta divided by cos theta, that's the same as having opposite over hypotenuse divided by adjacent over hypotenuse. How do you divide two fractions? You do the numerator fraction multiplied by the reciprocal of the denominator fraction. So that then we have O over H times H over A. And that equals OH over HA. Cancel the H's. And that equals O over A. Oh, we know what O over A is. That's tan theta. So mu equals tan theta at the slipping point. We can draw a quick sketch of a tan curve with my very nice axes. Something like that. And we can have the asymptotes at minus 90 and at 90. And this is mu, and obviously this is theta. And we can see, looking at this curve, hang on, so if mu is bigger, then the slipping point happens at a steeper angle of theta, which makes sense intuitively. We can also see that no matter how high mu gets, the slipping point is always going to be below 90. The curve never hits 90, because obviously if it's vertical, like this, there's no reaction force. There's no vertical component to the reaction force, I should say. So this curve, when we look at it, we know that our formula here, we know that's got to be right. And we can also Google it and double check that the maths is correct. And it is. Yes, I did work that out myself. Just playing with numbers, but don't worry, I have Googled and it's right. Other people have done this before me, obviously. Right then, it's now time to find the coefficient of friction for a lemon. I'm going to do it for a wet lemon and a dry lemon because I believe in scientific rigour. This is the point in the video where you're going to think, bloody hell. What I've done is I've taped a lemon, which I've cut, to a Portman plotter, and I'm going to push it up against the door, balance the 20p on it, and turn the dial on the plotter until the 20p slips. I'll have the angle, and I can record that. I'm going to do it 6 times, 3 turning it clockwise, 3 turning it anti-clockwise. No, I don't think it's going to make a difference, but, you know, why not? And then I'll take the mean of the 6 attempts. Now you might be thinking, 6 isn't a very big sample size, Douglas. You could be more accurate with this. That's right, I could. However, I'd like to remind you that I'm trying to find the coefficient of friction between a 20p and a lemon, so let's not get too carried away, he says. Right, let's give this a go. I've not tried this yet, so it might fail spectacularly. Right. So we need to make sure that the Portman plotter is set to 0, which it is, and it's vertical. Now, which it is, we balance the 20p on the lemon. I'm trying to get it as square as I can. Yep, there we go. Now I'm going to turn the dial very slowly. Which way am I going to do it? Clockwise first. $15, 20 degrees. There we go. What was that? 24.5 degrees. So I'll write that in my notepad. 24.5 degrees. I'm going to do the... Right then. In the end, this is dry. And I didn't bother doing wet because I'm going to assume that if you're doing this in the pub, we're going to assume that the top of the lemon has air dried, and we're going to assume your pockets aren't wet either. So just use a dry coin and a dry lemon. And I did one more in each direction than I said I would. This isn't a proper thing, obviously. It's very unlikely you're still watching. Yeah, so 2, I'm going to say, is an anomaly. I'm going to cross that one out. All the rest of them, I think, are fine. So we're going to try and find the mean. So 24.5 plus 25.5 plus 26.5 plus 26.5 plus 20 plus 21.5 plus, that should be a plus 24 divided by 7 equals, okay, so that equals 24.1 degrees. We know that mu equals tan theta, so if theta is 24.1, tan 24.1 equals 0.447. So that's mu. That is the coefficient of friction between a dry 20p and a dry lemon. There we go, we've got that. Now, how can we cheat is the question. And I think the way you do it is by adding more mass to the bottom of the coin to bring the center of gravity of the lemon below the center of buoyancy. And as I say that, ignore me. You need to bring the center of gravity below the center of buoyancy. I fear that if I try to do that, the lemon might sink, but it's worth giving it a go. So we're going to try and do that. So what we can imagine if we bring the center of gravity below the center of buoyancy. So center of buoyancy is here. Center of gravity has been brought down to here because we've got all this mass here. What would happen if we added a coin to the top? Like this. Now that would upset the center of gravity and move it over here. So now our lemon looks a bit like this. So we can see we have a healing moment going clockwise. As it moves clockwise, G is going to move under B and it will settle. If we can get it to settle so that theta is less than 24.1 degrees, then the coin won't slip off, is the theory, because the lemon will be made sufficiently stable due to the fact that gravity is below buoyancy. I haven't tried this yet. I'm going to try it now. If it doesn't work, I suspect the problem is going to be I'm not going to be able to add enough mass to the lemon without it sinking, but we'll give it a go. Right then, what the blazes have I done, you ask? Well, I took the lemon and I cut a hole in the bottom of it, hollowed it out a tad, added a 20p as ballast, put the lid for the hole back on, smeared it with loads of Vaseline to try and make it watertight, and then electrical taped it. And now you can see the lemon barely float. This might not work. It floats quite high actually, given that there's an extra 20p in there, which is good and bad. Right, now let's see if we can balance the 20p on now that I've weighted the lemon. No. And of course, now the lemon is wet and the 20p is wet, so my my angle of 24.1 degrees is, and my coefficient of 0.44 isn't quite accurate. Yeah, I may have failed here. Yeah, this is not going to work. Every time I try, the water gets bumpier. Yeah, I can't be bothered anymore. Obviously, this has already taken up way too much of my time and your time. I could fiddle with the lemon. I could completely hollow it out and add 20p to the bottom, but I really cannot be bothered. So that's it. Yeah.
So it turns out that even if you are going to take things too far, and you can do the maths to work it out, and you are willing to cheat, you can't balance a 20p on a lemon. I mean, I'm sure you could, but ultimately there are too many factors, lemon buoyancy being one. So I've not won a pint, but then, let's be honest, I'm just sitting in my room on my own, so there wasn't a pint up for grabs anyway. So I think I'll go to the pub and have one, because why not? Sorry for wasting your time.